Hi, welcome to Unit 5, Day 11. This is a review day of chemical reactions. In part 1, we're going to review week 1 from Unit 5 and synthesis, decomposition, and combustion reactions. All right, so in Unit 5, we learned about chemical reactions. In the first week, we learned some basic concepts. We learned what happens during a chemical reaction. We learned about kinetics, which is the study of rates of reactions. And we did a lab which we explored 5 factors that influence the rate of a chemical reaction. We also learned some thermodynamics, which discusses the energy changes during the reaction. And there are two main types of reactions that we look for at there. Endothermic reactions, where the reaction gains or absorbs heat, and so the surroundings, like your hand or the air, will feel cool. And exothermic, where the reaction loses or releases heat, and the air or your hand around it will feel hot. We also learned how to balance chemical reaction equations. In the second week, we learned about the types of chemical reactions. So let's take a moment to review what we did in the first week. So the first thing we learned about was what happens during a chemical reaction. And during a chemical reaction, bonds in the reactant are broken and new bonds are formed. So you break bonds and form new ones to make your product. Now, breaking bonds requires energy, and forming bonds releases energy. And so that leads us into the concept of thermodynamics, which studies the energy changes during a reaction. So as we said before, there are two types, endo and exothermic. During an endothermic reaction, more heat is absorbed or gained in breaking bonds than is released in forming bonds. And so overall, you have an overall absorption of energy. And so it's going to feel cool. And we also saw the reaction profiles for endothermic reactions. So since the system or the reaction is gaining energy, the product, the P, is going to be higher than the reactant R. We also learned about enthalpy, which is delta H. It is a way of representing heat. So for endothermic reactions, since the system is gaining heat, it's going to be a positive change. So delta H will be positive. For exothermic reaction, the opposite is true. In an exothermic reaction, more heat is released in forming bonds than is absorbed to break the bonds. And so in this case, the change in heat energy, delta H, since you're losing, will be negative. So that delta H will be negative, and those reactions will feel hot, right? Also, we looked at its reaction profile. Since you're losing energy, the product will be lower in energy than the reactants. The other thing we learned about is kinetics. So kinetics involves the study of reaction rates. And we looked at 5 factors that affect reaction rate. There's concentration, temperature, surface area, agitation or stirring, and adding or not adding a catalyst. So these are all things that can affect how fast or slow a reaction is. For example, if you wanted to slow down a reaction, maybe you would lower the temperature or stop stirring it. If you wanted to speed up a reaction, you would increase the concentration or amount of reactants that you used, or you could add a catalyst. The last thing we looked at was chemical reaction equations. So we learned how to read a chemical reaction equation like the one shown at the bottom here. The reactants are going to be written on the left and the products are going to be written on the right. Then we learned that we have to balance a chemical reaction equation according to the law of conservation of mass. And that means that you have to have the same number of each type of atom on both sides of the reaction arrow. So the same number of each type of atom on the reactant and the product side. Now, to balance a chemical reaction equation, we have to change the coefficients, which are the big numbers in front, which tell you how much of each molecule or species you have. And when you change them correctly, you should get the same number. So that's what we learned in the first week. For the second week, we learned about types of chemical reactions. And there are 5 types of chemical reactions. And the reason why we learn about these types of chemical reactions is because it allows us to predict the products. And also, sometimes knowing the type of reaction we have, we can use strategies to balance a chemical reaction equation. Okay, so for the 5 types, sometimes you actually have to know how to predict the products. In all of them, you need to know how to balance them, but some of them have strategies. So what exactly do you need to know for each one? That's what we're going to go over here. And we're going to start with synthesis. So in a synthesis reaction, we have two or more types of reactants that combine to produce one product. And here's an example. We have two reactants, H2 and N2, combined to produce NH3. Now, what you need to know for this is you don't need to know how to predict the products. Like if I gave you H2 and N2, you don't need to know how to predict that the product will be NH3. But you do need to know how to balance it. And luckily, it's balancing like normal. There's no real strategies here. For decomposition, it's the opposite of synthesis. In decomposition, you have one reactant that breaks apart or breaks down into two or more products. So here we have the decomposition of sodium bicarbonate, also known as baking soda. Now, once again, here you don't need to predict the product. So if I gave you baking soda, I'm not asking you to predict what the products are going to be, but you do need to know how to balance it. And again, you balance it like normal. So let's do a couple of CFUs here. So I'm asking you to label each reaction as synthesis, decomposition, or neither, and then explain why you chose that. And in your explanation, you can go back to the definitions that are here. All right, so go ahead and pause the video now. When you press play again, the answer will be revealed. Okay, so the first one is decomposition. We have one reactant that's broken down into two or more products. Second one is synthesis. We have two reactants that make one product. The third one is neither. We have two reactants and two products, so we know that that can't be synthesis or decomposition. And the last one is synthesis. We have two or more reactants that make one product. All right, let's now go over a combustion reaction. So a combustion reaction, we focus on the combustion of organic molecules, but in general, a combustion reaction is a reaction that involves something reacting with oxygen and producing an oxide, a product that's an oxide. But here we just focus on the combustion of organic molecules, and organic molecules are carbon-based molecules. Now, in the combustion of an organic molecule, the organic molecule will react with O2, and it makes two products, H2O and CO2. So here's an example of that. This is the combustion of octane to produce CO2 and H2O. So a couple things. O2 must always be a reactant, and CO2 and H2O must be your products. Now, the reason why CO2 and H2O must be your products is because we're focusing on complete combustion of organic molecules. And for complete combustion, CO2 and H2O are the products. Now, these reactions are, they release heat. They're hot, right? So they're exothermic. And combustion reactions are the reactions that we see when we turn on a gas stove, for example, or burning any sort of fuel. That's an example of a combustion reaction. So what do you need to know how to do for this? First, you need to know how to recognize it. For all of these, you need to know how to recognize what type of reaction it is. But you also need to know how to predict the product. So you need to know that CO2 and H2O are always the product, and O2 is always the reactant. Finally, you need to know how to balance it. And there are a couple of strategies that we went over with this. So firstly, you want to balance oxygen last. And you want to make sure your coefficients are the smallest number possible and no decimals. Now, those rules about the coefficients are true for all reactions, but it really is something that shows up in combustion. So that's why we sort of took a moment to go over it then. All right, so let's take a look at this CFU. Which of the following reactions represent a combustion reaction? So pause the video now, and when you press play again, the answer will be revealed. The answer is C, and that's because O2 is a reactant and CO2 and H2O are the products, along with your organic molecule, the carbon-based molecule. These explanations explain what the other reactions are as well. Okay, now for CFU3, I'm going to ask you to write the equation for the combustion of C6H14. So if you're not sure how to handle this, in about 3 seconds, you're going to get a basic hint to get you started. If you do know how to handle this, go ahead and pause the video, and when you press play again, the answer will be revealed. All right, if you need a basic hint, here is your hint for that. So the first thing you want to do is write the unbalanced equation. So you're going to write your reactants on the left side and your products on the right. So you'll need to know what reactants and products you have for the combustion of C6H14. The second step you want to be able to do is then balance it. So if you need more support, if you know what to do now, you can go ahead and pause the video and go ahead and finish this problem. But if you need more support, there will be more support in about 3 seconds. All right, so let's go into some extra support if you need to. So in writing the unbalanced equation, your reactants should be your organic molecule, C6H14, and O2. So that you're going to write on the left side of the arrow. The products are going to be CO2 and H2O. After you have that written, when you want to go balance it, remember you're going to balance not just O2, but oxygen in general last. So all the oxygen you balance last. And remember, you can't have a decimal. So if you need to get rid of a decimal like 0.5, 1.5, 2.5, etc., you need to multiply all the coefficients by 2. Pause the video now. When you press play again, the answer will be revealed. Okay, so here's my first step. Here's my unbalanced equation with my reactants and products. Then to balance it, I need to figure out the coefficients that will get me the same number of atoms on both sides. So I count up the number of atoms I have on both sides. For me, I started balancing the carbons first. So I put a 6 in front of CO2. That changed the number of carbons to 6 and the number of oxygens to 13. Remember, when you do that, since oxygen is in CO2 and H2O, we would do 6 times 2, which is 12, plus the 1 in H2O to give me the 13. Then I balanced the hydrogens. So I needed to put a 7 in front of H2O, since I have 14 on the reactant side and 2 on the product side. And when I did that, that changed the number of hydrogens to 14 and the number of oxygens to 19. Now I'm ready to balance my oxygens. And remember, I'm balancing those last. So now I want to figure out what coefficient can I put in front of O2 so that I can get 19 oxygens on both sides. Well, I'm really asking myself 2 times what will give me 19? And the answer to that is 9.5. So I'm going to go ahead and put that in. I can't keep it because remember, you can't have a decimal, right? We can't have a decimal. So I'm going to have to get rid of that. But right now it's balanced. However, to get rid of that decimal, I need to multiply the 9.5 by 2. And remember, just like with math, whatever you do on one side, you have to do on both sides. So I have to multiply all the coefficients by 2. So I'm going to multiply the coefficient in front of C6H14, which was an invisible 1, by 2. And the other coefficients by 2. And then that gives me this as my final balanced equation. All right, last CFU here, or second to last CFU. Given the combustion reactions are exothermic, which of the following reaction profiles could represent the combustion of butane? Explain. So pause the video now, and when you press play again, the answer will be revealed. So for an exothermic reaction, remember that heat energy is being lost. So the products are going to be lower in energy, and energy is on the y-axis, than the reactant. And so that will be choice B, because the products are lower than reactants. All right. Last CFU, the reaction profile for the combustion of butane is shown. Use the information to calculate the delta H, the change in enthalpy. And then is the value reasonable based on the sign? Pause the video now. When you press play again, the answer will be revealed. All right, the answer is -24. So remember, to get the delta H, you need to get the difference in the reactant, which is the first flat line here, and the product, which is the last flat line. And so the reactants is about 34, estimated to be about 34. The product is about 10, and it's always products minus reactant. So it's going to be 10 minus 34 to give you -24. Now, let's say you didn't do that correctly and you got +24. Well, that wouldn't, if you got positive, it wouldn't make sense, because remember, for an exothermic reaction, it's releasing heat. So delta H would be negative, right? Because it's losing heat. So it's negative. So if you got a +24, you would want to flip the sign. You knew you made a mistake. And if you got a -24, as I got, then your answer makes sense. The sign makes sense because it's exothermic. So it should be negative. All right, that is it for this video. In part 2, we'll review single displacement and double displacement. Have a quality day.